Hi everybody, my name is Dr. Marcus Kitchen and I'm going to be talking to you about the imaging practicum that we're going to be looking at today. And we're going to be focusing on imaging the knee phantom. And we're going to be looking at what happens when you change the MAS, that's the tube current, and the kilovoltage, that's the kVp, and what happens to the image quality and also to the dose as well. Now, hopefully you'll be reading the experiment before you go to the lab. Make sure you do that. But also before we get started, I'd just like to thank specifically Dr. Russell Horney and Dr. Rhiannon Murray for all their help in putting this practicum together. Thank you. Yeah. Okay, so firstly we're going to be looking at how to measure the dose using the DAP meter. So this is what our DAP meter looks like, and it basically sits in just underneath your X-ray tube, just like so, and the X-rays go through the DAP while you're exposing the patient. So what actually is a DAP meter? Well, DAP, D-A-P, stands for dose area product. So we're actually measuring the product of the dose in joules per kilogram multiplied by the area of the beam inside this ion chamber. So the units are in grey multiplied by units of area. So if we have a look at the measuring device, we have a display panel up the top, and that gives us our units. In this case, for this specific instrument, it is in centigrade times the area. So that dot is a multiplication symbol, so it's times the area of the beam. So why do we want to measure dose? Well, obviously dose is very important for the patient, but it's also important for keeping you safe and for designing radiation safety for the whole environment that we're in. Also, it's very important for the detector itself. So really what we're measuring is not only the dose to the patient, but actually to the detector itself as well. Many detectors have a lot of electronics in it that need to be shielded and protected from radiation, which can damage the electronics as well. So measuring dose is important for multiple facets. Okay. So how does a DAP meter work? Now, I'm sure you remember from previous lectures about how an ion chamber works, and this is essentially an ion chamber. It's a gas-filled chamber. So what we see in the device is some metal strips around the outside. Hopefully you can see those here. And it's basically plastic covering on two sides, and inside it is just air. That air is going to become ionized in response to X-rays, which are of course ionizing radiation. So as the X-rays transmit through here, some of the atoms are ionized by Compton scattering or by the photoelectric effect. So in other words, some of the energy of the X-rays is absorbed and that liberates charge. So those charges are now free to move around in our ion chamber. And because these plates have also been charged, any negative charges will be attracted to a positive terminal and positive charges will be attracted to a negative terminal. And so now we have charge flowing through the ion chamber. That charge can flow through the circuit into our meter when that is connected, and we can measure a current. So we're basically measuring ionizing effect as a current, and that in turn can be converted to a dose. So while we're imaging the knee phantom, we're going to be changing the MAS and the kVp and measuring the effect on dose. Now, the main benefit of using a dose area product meter like this is that the dose area product is basically independent of where we put the ionization chamber within the field path. That might seem counterintuitive because, as you've been taught, the X-ray beam is expanding as it propagates away from it. And you should know that the intensity of the beam will be reduced as the inverse square law. So the further away we get from the source, the weaker the beam is going to be. That also means that the weaker the dose is going to be. So in other words, if I have my tissue in here, the amount of ionizing radiation, the amount of energy deposited per unit mass is going to be reduced the further I get away from the source. But really what's happening is that the number of X-rays are not reducing as we get further away from the source, because the area of the beam is also increasing. So the dose area product meter measures a reduction in dose as we get further away, but because the beam is expanding in size, as long as the beam still fits within the field of view of the DAP meter, then that product remains constant. So it is independent of source to object distance. So that's it for the dose side of things. But what happens when we're actually talking about the image quality? how does MAS and KVP affect image quality? Now, most systems these days are digital. This is an example of a CR cassette from AGFA. As you hopefully know by now, that once the cassette is exposed, it is sent into a CR readout system, and the image becomes digitized like this, as we see here. So in order to measure the effect on the image quality of MAS and KVP, manufacturers have come up with something called an exposure index. Now this is often displayed on the screen. You can see here the EI, that is the exposure index that comes with each image. This does not tell us about the dose to the patient. If anything, it tells us a bit about the dose to the actual CR plate itself, but not directly to the patient. It is a measure of how good the image quality is in terms of the grey levels in the image. So each image should have a certain range of grey levels for the image quality to be acceptable. If the image is too noisy, the exposure index will reveal that. Also, if the dose to the actual CR plate is too high, even though the image quality will be very good, the exposure index will also show that up as well. So now the next question is, what is the actual exposure index and how is that calculated? Each manufacturer has their own different algorithm for calculating the exposure index, but basically all of them use the same rough principle. So we take our image like this, and we generate a histogram that is an intensity distribution or probability density function of all the different grey levels in the image. And that will look something like this. So we can see here that there's a lot of bright values, but also a lot of dark values in the image as well. To calculate the exposure index, we normally throw away areas where it's overexposed or underexposed, and just focus on the main levels of grey scale that are in the image. And we calculate the median of this histogram in order to then go on using some algorithm specified by the manufacturer to calculate the exposure index like this. Now, one of the problems with having a different exposure index for each body part or between manufacturers is that it doesn't give us a general feel of what the actual exposure is. And so you might learn what a satisfactory exposure index is for one manufacturer, and it'll be very different for a different manufacturer. So this is why the International Electrochemical Commission has come up with something called the deviation index instead, which you may see from time to time. So that's given the acronym DI instead. And that is one algorithm that all manufacturers must use. But most of the time you're still going to come across these exposure indices which are going to be specified for a specific manufacturer. And for each different anatomical body part, they'll have an ideal EI value for each anatomical part for that specific type of system that you're employing. So, now for each body part, every manufacturer will have its own ideal exposure index. And you can look at the chart to see if your exposure index is in the right range. One of the problems with having many different manufacturers having their own exposure indices and their own algorithms is that if you're used to using one particular system and then you change to a different system, the exposure indexes will mean something completely different. So the International Electrotechnical Commission came up with a strategy of having a single algorithm that all manufacturers can use, and they call this, instead of the exposure index, they call it a deviation index. So that is something that you will see from time to time, and increasingly so in the future. But you need to be aware that still currently in Australia, many manufacturers still use the exposure index. And you'll need to have a chart that is relevant for that specific imaging system and also for the specific body part that has an appropriate exposure index. Now the exposure index, as we've talked about, can change dramatically with MAS and KVP, but there are many other factors to consider as well. For example, your source to image distance is going to change the intensity of your beam. The collimation of the beam is also going to change the exposure to your film plate. Then there's other things that, for example, like anti-scatter grids and the size of the patient, and even the positioning of the patient, where exactly that is on your film plate, is going to change what your exposure index will read out. So you have to be aware of all these many factors. So the main focus of the experiment now is to look at how exposure index changes with MAS and KVP. Now hopefully you remember from lectures how the MAS changes the exposure to the patient as well as to the detector. and that there should be a linear relationship between MAS and your dose to the patient. KVP, however, is a lot more complicated. Changing the KVP changes the energy range of your X-rays. It also changes the number of X-rays produced and also changes the dose distribution. So have a think about how you expect that the number of X-rays and how the KVP changes is going to affect your exposure index. Keeping in mind that at lower KVPs you have lower penetration power, therefore lower number of X-rays getting through the patient, whereas at higher X-rays you're getting more penetration through the patient. And also it's a non-linear relationship between KVP and exposure. So good luck with your experiment.